Hey everybody, so here's the final exam review for you. It's on chapters 6 and 7 only. Remember, I said this time that the final exam would not be comprehensive. However, do bear in mind that you still have to understand things from earlier in order to be able to do this. So while you're not going to be explicitly tested on anything other than chapters 6 and 7, that doesn't mean that you won't need that knowledge in order to work some problems. So make sure that you understand the earlier material as well. Okay, so starting off in chapter 6, we defined what's known as a Boltzmann factor. And the Boltzmann factor can give you the relative probability of different energy states for a system at a given temperature T. So the Boltzmann factor can be written as E to the negative energy of the state divided by KT. And of course here K is Boltzmann's constant, 1.38 times 10 to the minus 23 joules per Kelvin. So that's the SI units. So if you have two different energy states, and we'll call them state 2 or S2 and state 1 or S1, then the ratio of the probabilities of those energy states, the probability of state 2 divided by the probability of state 1, is the ratio of the Boltzmann factors for those energy states. And when you take those ratios, then what you end up with in your exponent is the difference in energy in between those states. Now, of course, if there's a degeneracy to those energy states, then what you would do is out front, you would multiply the degeneracy of the state times the Boltzmann factor before taking this ratio. So this little expression here just assumes that neither of the states are degenerate, okay? Now sometimes here and in your book, in order to make things a little more compact looking, we will use the shorthand beta, and beta is 1 over KT. So from this expression, we derived the probability of a state S when a system is allowed to draw energy from a reservoir. So here we're allowing a system to draw and deposit energy into a reservoir, and they're maintained at a temperature T. They're in thermal equilibrium at a temperature T. So the probability of the energy state S is equal to 1 over Z times e to the minus es over kt. So it's 1 over z times the Boltzmann factor. Now this is the Boltzmann distribution function. Sorry about that typo. There you go. This is the Boltzmann distribution function. And here z is known as the partition function. So you find your partition function by summing over all the possible states for their Boltzmann factors, e to the minus es over kt. Now, Boltzmann statistics, they work for classical systems like ideal gases. And this is what we call the canonical ensemble. And in a canonical ensemble, the system is in thermal equilibrium with a reservoir and can exchange energy with that reservoir. Now, in that partition function, remember that you're summing over all the states. So you can have multiple states with the same energy. That's known as degeneracy. If that's the case, then that Boltzmann factor would appear in the sum multiple times. So what you do practically when you're solving for the partition function is you multiply your Boltzmann factor times the degeneracy and then sum over all the different energies doing that. Okay? Now remember that this is a distribution function. We went over some of the rules for distribution functions. And one of those rules is that if you want to find the average value for any variable, we'll just say we want the average value of some random variable x, then all you do to find the average is you do 1 over the partition function times the sum over all the states of the value of x for that state, x of s, times the Boltzmann factor. Okay? And that's just how distribution functions work. That's just the math of distribution functions. And so that means that if you wanted to calculate your average energy on a per particle basis, then E bar would be 1 over z times the sum over all states of the energy of that state times the Boltzmann factor. Okay? And for the entire ensemble, then that means that you would multiply the number of particles in the ensemble in times the average energy per particle, E bar, and then that would give you U, which is the internal energy of the system. Okay, now remember that for ideal gas molecules, you can describe things like nitrogen and oxygen, which are in air, of course, by the Boltzmann function. However, at room temperature, those particles rotate in addition to translate. And so sometimes you need to consider the rotational kinetic energy of your molecules in addition to the translational. If that's the case, then the energy of the rotational states can be written as h bar squared over 2I times j plus 1. Now remember here, h bar is Planck's constant divided by 2 pi. So that's Planck's constant is 6.626 times 10 to the minus 34 joules seconds, right? And then you divide that number by 2 pi to get h bar. Here I is the moment of inertia for the molecule that's rotating about its center of mass. J is the angular momentum quantum number, and J starts at 0 and goes up in integer steps from there. Now your book does use a shorthand here sometimes, and they use epsilon is equal to h bar squared over 2I, just to make things a little bit more compact. Now, of course, what happens is the particles will change energy between neighboring energy states. And if they do that, then they have to absorb or emit a photon of the energy equal to the energy difference between those states. So if you do the math and work that out, then that ends up being 2 epsilon j. Now remember that the partition function for the rotational energies, Z internal here, is equal to kT over epsilon. We solved for that. And that's for molecules like carbon monoxide, which are diatomic molecules, but don't have symmetry to them. In other words, they're two dissimilar atoms. For molecules like nitrogen and oxygen, which are the same, then that halves your partition function, right? And so for nitrogen, oxygen, that's N2 and O2. It's the same atom on either side. So you take half of the partition function for an asymmetrical molecule like carbon monoxide. So that's kT over 2 epsilon. We also derived in class some useful relationships that we used many times in various derivations. And that's that E bar, the average energy per particle, is equal to minus 1 over Z times partial of Z with respect to beta. And that's also equal to minus partial with respect to beta of the natural log of Z. Okay? We also showed in some derivations that the equipartition theorem only works well when the energy can be written as a function of the position or the speed squared. You would have a different equipartition theorem, in other words, if the energy were a function of just the plain old speed or just the plain old position, right? So it's only when it's a quadratic system that the 1/2 kT per degree of freedom works out. Okay, we also derived the Maxwell speed distribution function, and this says that the probability that a particle has a velocity v is equal to m over 2 pi kt to the 3/2 power times 4 pi v squared times e to the minus mv squared over 2 kt. Okay, so we derived that. Now from this distribution function, you can find the most probable speed, the average speed, and the root mean square speed. So the most probable speed is the square root of 2 kt over m. You did that one for homework. The average speed I derived in class, and that's the square root of 8 kt over pi m. And the root mean square speed we've derived before, and that's the square root of 3 kt over m. Now, this distribution function isn't symmetric. In other words, if you went at the peak and folded the function in half, then one side wouldn't lie atop the other side. It's asymmetric. So your maximum speed is less than your average speed is less than your root mean square speed. Now, to get at the full partition function for an ideal gas with n particles, we went through various steps and scenarios and derivations. So what we did for the Boltzmann and for the Gibbs factors, by the way, in Chapter 7, was we used the particle in a three-dimensional box as a starting point for all of our distribution functions. Okay? So basically, we envisioned our gas or our system or whatever being contained within a three-dimensional box. Okay? Now what happens is, since these particles exhibit wave-particle duality, then they have a wavelength, the de Broglie wavelength. And if they're confined, then what will happen is only the wavelengths that satisfy this condition, lambda is equal to 2L over N, only those will survive. Okay? All the others will have destructive interference and cancel out. So here, big L is the length of the box in one dimension. And of course, that would hold in all three dimensions. So de Broglie wavelength, lambda is equal to h over p. So you can see that the momentum, p, you can rearrange that, would be equal to plus or minus h over lambda. And the particle would be going, say, for example, here, left and right. Right would be positive and left would be negative. Now, from this momentum expression, what happens is inside the box, we've got no annoying potential energies. We only have kinetic energy. And then at the walls of the box, the potential energy goes to infinity, and so it can't escape the box. So that means that all of the energy of the particles inside the box is kinetic. So you can say p squared over 2m and solve for the energy levels, and that gives you h squared n squared over 8ml squared for your energy levels for a 1D box. Okay? Now remember that your Boltzmann distribution is valid for only classical particles. What happens is if the particle spacing is much larger than the de Broglie wavelength, then you can consider it to be an ideal gas. And remember that if you start cramming them in and those quantum wave functions start to overlap one another, then you have to do your Fermi-Dirac or your Bose-Einstein distribution functions, because it's not valid for a classical setup anymore. So what you do is you compare your de Broglie wavelength to your particle spacing, or what we defined as the quantum length, which is very close to the de Broglie wavelength. Our quantum length L sub q is Planck's constant h divided by the square root of 2 pi mkt. And here m is the mass of a single particle, okay? Not the molar mass or whatever, but the mass of a single particle. Then the cube of the quantum length is the quantum volume. And so that is the volume that you would expect it to occupy, a single particle to occupy in 3D space. And like I said, as long as the spacing in between the particles is such that their wave functions don't overlap, then you can use the Boltzmann distribution function to describe it. If they start to overlap, you have to use one of the quantum distribution functions, either the Fermi-Dirac or the Bose-Einstein. So we derived the partition function for an ideal gas of n particles, and it's written here, z, the partition function, is equal to 1 over n factorial times v, z internal, over the quantum volume to the n power. Now here v is the volume of the container or whatever that the gas is in. Z internal is that rotational energy partition function that we had back here, okay? VQ is the quantum volume, of course, and N is the number of particles. Now, it's more useful sometimes to write the expression for the natural log of the partition function, ln of Z, and so we wrote that out, just expanding it. N is equal to the log of V plus the log of Z internal minus the log of N minus the log of VQ plus 1. Now, what we did is we used the free energy F, which is equal to minus kT times the natural log of Z. We derived that expression. And, of course, F is defined as U, the internal energy, minus TS. And so what we did here was we used that log of Z expression, okay, and then we found the free energy. And then we used the definition of the free energy, U minus TS, to derive the Sackur-Tetrode equation, okay. And so here, of course, what you would do is you would say that your partial of your free energy with respect to the temperature would be equal to your entropy expression. And there's how we got our Sackur-Tetrode equation for the entropy of an ideal gas. We also derived the chemical potential for an ideal gas. Okay, so that was Chapter 6. Now moving on, we didn't cover all of Chapter 7. We did what we could here, but I'll cover in this brief review what you're expected to understand and know for the final exam. Okay, so Chapter 7 dealt with Gibbs factors. So in Chapter 6, we dealt with Boltzmann factors. In other words, we had a system in contact with a reservoir, and we allowed it to exchange only energy. But in Chapter 7, we allowed the system to exchange both energy and particles with the reservoir. And so that meant that instead of Boltzmann factors, we used Gibbs factors. The Gibbs factor is equal to e to the minus es minus mu n of s over kt. Now here, E sub s is the energy of the state, like before. Mu is the chemical potential that we previously defined, and n of s would be the number of particles in that state. Okay, n of s. So the Gibbs factor, again, will give you the relative probabilities of the energy state given the temperature T. Okay, so we found those ratio of probabilities like before, except now, instead of Boltzmann factors, it's Gibbs factors on the top and the bottom there. And using that expression, we derived the grand canonical ensemble. Okay, so the grand canonical ensemble, again, is used when you're allowing the system to exchange both energy and particles with a reservoir that's held at a certain temperature T until it comes to equilibrium, okay? Now the probability of the state, P of s, is 1 over funky z times e to the minus es minus mu n of s over kt, okay? So that's 1 over the grand partition function times your Gibbs factor, all right? And the grand partition function is the sum over all the states of the Gibbs factors. We also derived the grand free energy, which is sometimes called the grand potential. So this is the Chapter 7 analog to the free energy F, right? This is the grand free energy. So that's usually symbolized with a capital phi, and that's minus kt times the natural log of funky z, right? And then the grand free energy phi is equal to F minus mu n. And then that means that we derive this little expression, the average number of particles n bar is equal to kt over funky z times the partial of funky z with respect to mu. Okay, now we reviewed some of the physics for fermions and bosons and some of the definitions for those things. So in order to do that, we had to review the concept of spin. So remember that spin is the intrinsic angular momentum that a particle possesses. So it's kind of a wrapping the head around it moment, but you have to realize that subatomic particles have an intrinsic angular momentum, just like they have an intrinsic mass or an intrinsic charge. Okay? You can visualize it if you want to as a particle spinning on its own axis, but that's really not the reality of it. So the magnitude of this angular momentum spin, which is symbolized usually with an S, is h bar, Planck's constant over 2 pi, times the square root of s times s plus 1. So capital S is used to symbolize the total spin angular momentum. Lowercase s is the quantum number associated with that angular momentum. So for an electron, s is equal to 1/2. It's also equal to 1/2 for protons and for neutrons as well. And of course, fermions are classified as half-integer spin particles. Okay? Now the magnetic quantum number for spin is plus minus 1/2. And the plus part is usually considered quote-unquote spin up, and the minus part is quote-unquote spin down. Okay? Okay, so fermions obey the Pauli exclusion principle, and their statistics follow the Fermi-Dirac distribution function. So remember that the Pauli exclusion principle states that no two electrons or no two fermions can ever be in the same quantum state if they are in the same potential well. Okay? So what that means is that no two electrons in the same atom, for example, can have the exact same set of quantum numbers. And this explains the structure of the periodic table. Now, if the exclusion principle wasn't true, then what would happen is all the atoms in the periodic table would all be in the same quantum state, right? All the electrons within each atom would all be in the lowest possible energy state. They would radiate that energy away until they were all in that, 1s orbital. But that's not what happens, so they have to stack up because they can't be in the same energy state. So although Pauli originally derived this for atoms or for electrons within an atom, it turns out to be valid for fermions occupying the same potential well. So we can apply Fermi-Dirac statistics to different systems. And the first one that we applied it to was the free electron gas. So as you may recall, electrons within a metal are free to roam around. So each atom in a metal, for example, in silver, for example, it donates 1 electron per atom to this free electron sea, and then those electrons roam all around the metal freely. And it explains a lot of the properties of metals, their conductivity, their luster, their malleability, their ductility. Okay? So the Fermi-Dirac distribution can be applied to those. So for example, here is the Fermi-Dirac distribution function, NFD. It's equal to 1 over 1 plus epsilon minus mu over KT. Now, if epsilon over mu is much less than 1, then what that means is that that distribution goes to 1. So, for example, if your energy is a lot less than your chemical potential, then you're going to have those low energy states, and they're always going to be occupied. Now, on the other hand, if your energy is a lot greater than your potential energy, than the chemical potential, then the distribution dies off and goes to 0. And so that means that very high energy states are not going to be occupied. All right? Now, as the temperature of the system tends toward absolute 0, so as KT goes to 0, then the distribution function starts looking a lot more like a step function. Okay, so that's pictured over here in this little graphic. Here we have KT is equal to mu over 100, so it's really cold, and you can see that that's that sort of cyan curve, so it's more like a step function. But as KT gets closer and closer to mu, the distribution function starts to round off and then eventually look more like a decaying exponential, okay, where KT is equal to mu. But for room temperature, for example, we can still use the approximation that KT is very close to 0, and there's only a slight rounding for electrons in the free electron gas, for example, and it looks very step function-like. Now, at 0 Kelvin, the highest occupied energy state we call the Fermi energy, of course in honor of Enrico Fermi, who was one of the ones that pioneered this distribution function. And so the Fermi energy is the highest occupied state at 0 Kelvin. And so that means that we would write our Fermi-Dirac distribution function as 1 over e to the epsilon minus e Fermi over KT plus 1. Okay, so basically mu and e Fermi are interchangeable for these free electron gas scenarios. Now we derived an expression for the Fermi energy, and that expression, I don't expect you to be able to recreate these derivations, of course, but I do expect you to be able to use these expressions that we derived. So the Fermi energy is h squared over 8m times 3n over pi v to the 2/3 power. Okay, so remember how to find the Fermi energy for different materials. Remember that m here is the mass of an electron in this case. Now, the internal energy for the whole system, the collection of n electrons, for example, would be 3/5 n times the Fermi energy. Okay, and this is the average energy at 0 Kelvin. We also calculated the degeneracy pressure of this degenerate Fermi gas, and that was using the formula P is equal to minus partial U with respect to V, holding entropy and number of particles constant, and we ended up with 2n E Fermi over 5V, which is 2/3 U over V. The degeneracy pressure is, of course, due to the Pauli exclusion principle. In other words, if you start trying to cram things together too tightly, then you're almost trying to force those fermions to be in the same energy state, and they're resisting that. They're pushing back. Okay? The bulk modulus is the change in pressure when the material is compressed, divided by the fractional change in volume. And we solved for this for our system. So the bulk modulus B is equal to minus V partial P with respect to V, holding the temperature constant. And then that's equal to 10/9 U over V. So then we introduced a rather tricky concept called the density of states. The density of states is often written as G of epsilon. The density of states, what it means is it's the number of states per unit energy. Now the expression that we found for the density of states was pi times 8m to the 3/2 over 2h cubed times the volume V times the square root of epsilon, the energy. Now the density of states can be used to find the number of particles at 0 Kelvin. So if you just integrate from 0 to the Fermi energy, your density of states, G of epsilon with respect to epsilon, then you're going to find the total number of particles at 0 Kelvin. But of course, if your temperature is higher than 0 Kelvin, then you have to multiply the density of states times the Fermi-Dirac distribution function. So then n would be equal to the integral from 0 to infinity now, right, times the density of states G of epsilon times the Fermi-Dirac distribution function n fd of epsilon d epsilon. And you can also find the energy for temperatures greater than 0 Kelvin using that same idea. But remember that for distribution functions, you have to multiply the value, right, times the distribution function in order to get that average. So here U is equal to the integral from 0 to infinity of epsilon times G of epsilon times NFD of epsilon d epsilon for T is equal to 0, greater than 0 Kelvin. Okay? Okay, so that's enough on fermions. Let's talk about bosons. Bosons are integer spin particles. Okay, they can be composite particles where the total spin is an integer like helium-4, which of course we talked about liquid helium and the superfluid helium and all that good stuff. Okay, so that's a composite boson because helium is composed of 4 fermions, but if you add up their intrinsic angular momentum, then you end up with an integer value because there's an even number of particles. Okay, you can also have bosons be particles by themselves. So there's some particles that you might see in high energy physics like pions that have integer spin. All right. Also, the exchange particles for all the 4 fundamental forces of nature are bosons. So you have the W and Z boson, which is the carrier particle for the weak force. The gluon is the carrier particle for the strong force. And the photon is the carrier particle for the electromagnetic force. And the graviton is the carrier particle for the gravitational force. All of those are integer spin particles, so they're all bosons. Now, it might be hard to understand, but photons, light, of course, particles of light, they are integer spin. So they have a spin 1. So students often have a hard time understanding that photons can have momentum even though they don't have mass. Well, okay, if you wrap your head around that, add another one. Photons can also have angular momentum even though they don't have mass. And it comes from the polarization of the electromagnetic field of the photon. So it can either be right circularly polarized or left circularly polarized. And then all other polarizations are just sums of those 2 categories. Okay? So the Bose-Einstein distribution function is given by n sub BE is 1 over e to the epsilon minus mu over kt minus 1. Okay? Now, if you look here, we have plotted in this figure the 3 distribution functions that we covered in chapter 6 and 7, the Bose-Einstein, the Maxwell-Boltzmann, and the Fermi-Dirac. The Fermi-Dirac here is in red, and you can see it looks like a rounded off step function. And your Maxwell-Boltzmann and your Bose-Einstein are a lot closer looking to each other. The major difference is that as for the Bose-Einstein distribution, as epsilon approaches mu, the average occupation of the state approaches infinity. Since that's impossible, because there's not an infinite number of particles, there's a restriction on the values of epsilon, and that's that epsilon has to be greater than mu always, okay? And what happens is, of course, that at low temperatures, all the particles are going to pack into the same lowest energy state, okay? And, of course, at high temperatures, all of the distribution functions converge out here. You can see that at this point, they're all overlapping as the temperature gets higher and higher. And that makes sense because quantum particles start to behave classically as the energy gets large. So we use the Bose-Einstein distribution function to describe a couple of different systems. One of those was black body radiation from a black body radiator. So to review, a black body is an ideal system that absorbs all the radiation incident on it. Of course, the opposite of a black body would be a perfect reflector. And what happens is objects emit a spectrum, an electromagnetic radiation spectrum, that's solely based on their temperature. And so, you might know that you emit radiation in the infrared because you're 98.6 degrees Fahrenheit, okay? So it's the temperature of the object that dictates what radiation frequency it emits. And this is black body radiation. So you can see human beings with infrared goggles, even if it's dark out, for example. So this black body radiation spectrum is a characteristic shape, and there was a big problem in the 1800s describing why the black body radiation spectrum had the shape it does. And classical physics failed. This is known as the ultraviolet catastrophe, and it doesn't work well for normal temperatures. It only works at high temperatures, the classical description. And then Planck came along and developed a model of black body radiators where he envisioned these atoms in the black body, the solid body, connected by bonds which he modeled as springs. And basically he said that what happens is that these black body radiators can jump in energy levels, and the energy levels are quantized. And the quantization of the energy is NHF, where H is Planck's constant, F is the frequency of vibration, and N is the energy level. And so the photons that are emitted or absorbed by a black body radiator are causing this jump in energy level in between states. Okay, so that's what Planck did. And he derived a theoretical expression for the wavelength distribution of a black body radiator based on this idea. And what he said was that the intensity I is a function of the wavelength and the temperature, varying according to the equation 2 pi hc squared over lambda to the fifth e to the hc over lambda kt minus 1. Okay? All right, now we derived this expression in class assuming the Bose-Einstein distribution function. So we started from the Bose-Einstein distribution function and derived Planck expression. Okay? And we had a lot easier time than Planck did. Now, some of the expressions that we also derived from this were what was known about black body radiators before Planck started his work, and those were Wien's law and Stefan's law. So if you take the derivative of that intensity and you set it equal to 0, then you'll get the wavelength where the maximum intensity occurs. So this is Wien's law. So it's lambda max times the temperature is equal to 0.002898 meters times Kelvin. So that's Wien's law, okay? It tells you where the location of the peak is on the black body curve for a given temperature. And then if you use the expression for the total energy density, then you can derive the Stefan-Boltzmann law. So in order to do that, we first had to define the total energy density, and we solved for that. And U over V was equal to 8 pi to the fifth kt to the fourth over 15 hc cubed. Okay, we derived that expression for the energy density. And then we could also get the heat capacity by taking the partial of U with respect to T, and we found the heat capacity for these photons. So that CV is equal to 32 pi to the fifth k to the fourth VT cubed over 15 hc cubed. So we derived that as well. And then we also finally related it to the Stefan-Boltzmann law the Stefan-Boltzmann law said that the power emitted from a black body radiator was given by sigma A e t to the fourth. Now here, sigma was a constant, 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. T was the temperature, of course. A was the surface area of the object, and E was the emissivity. Now, the emissivity E is a measure of how good of a black body radiator something it is. If it's a perfect reflector like a spherical mirror, E would be equal to 0. It's not a good black body. But for like a black box with a little pinhole in it, it would be a perfect black body, and E would be equal to 1. And so if you play around with this expression here, you can convert and solve and show from the energy density expression that I showed you on the previous slide that you can predict what sigma is in the Stefan-Boltzmann law. Okay? Now the other system that we used for Bose-Einstein statistics was, of course, the Bose-Einstein condensate. Okay? So what happens is if you take a particle, it could behave classically at room temperature, like helium, for example. But then you chill it down and you get it colder and colder and colder until the material gets cold enough and dense enough so that the quantum wave functions of those particles overlap. Okay? And in that case, the material will transition, it'll go through a phase transition into a Bose-Einstein condensate. Now this happens to liquid helium. It was the first Bose-Einstein condensate found. Helium actually liquefies at 4 Kelvin, around 4 Kelvin, but then it undergoes a phase transition at the critical temperature for helium, which is 2.17 Kelvin, and it changes into a superfluid, which is a consequence of it being a Bose-Einstein condensate. Now, it's a little funny, helium is, because of course in helium there's different isotopes of helium. So there's helium-4, which can become a Bose-Einstein condensate at 2.17 Kelvin, but then there's also helium-3, which is it's not at a high concentration. I think it's only 1 in 10,000 or so, but it's still present. So you can't really call liquid helium at 2.17 Kelvin a true Bose-Einstein condensate for that reason, because there's a little bit of helium-3 mixed in there usually. Okay, but at any rate, it's close enough to behaving like a Bose-Einstein condensate because of the low concentration of helium-3 that it has certain cool characteristics that you saw in those videos. So the lambda point is what they call the critical temperature, and that's because of the shape of the curve of the specific heat versus the temperature, which is shown here. It looks like the Greek letter lambda. Some other cool properties of liquid helium at this critical temperature is that it has a super low viscosity, pretty much 0, okay? Yeah, so it has some really cool properties. Another neat expression that we learned was the London equation, okay? And the London equation gives the fraction of helium atoms in that superfluid state given the temperature. So F, the fraction, is equal to 1 minus T over the critical temperature, T sub C to the 3/2 power. We also derived this expression for the density N over V of a Bose-Einstein condensate. N over V is equal to 2.612 times 2 pi mkTc to the 3/2 over h cubed. And that's 2.612 over the quantum volume. So what this shows you is that the reason it behaves like a Bose-Einstein condensate is because there's 2 or 3 particles packed into that quantum volume, and that means that the wave functions overlap. Okay? That's why it starts behaving like a quantum particle instead of a classical one. And of course, pure Bose-Einstein condensates have been created in the labs, and if you want to look that up, it's really cool. People got Nobel Prizes for it. And the first success was with rubidium atoms at really low temperatures. So those were the pure Bose-Einstein condensates. And now they're used as model systems to explain early universe physics, among other really cool things. Okay, well, I hope that you're doing okay. Study, and we'll post that final exam next week. Okay, bye-bye.